So when we're looking at an object traveling in uniform circular motion, the net force is always mv squared on r. So that means that the net force on the car, our F net, is just going to be equal to mv squared on r, which is then going to be equal to our 1,000 kilograms times by our 14 meters per second squared, and we are going to divide that through by our radius of 50, which we can then get as being the 3,920 newtons. Done. If the coefficient of friction is 0.6, determine if the car would skid off the road. So there's two different options. You can solve for the coefficient of friction that meets that net force, or you can actually just solve to determine the maximum amount of friction force. So I'm just going to solve for the maximum amount of friction force. So I'm just going to look at my frictional force. Force of friction is equal to mu Fn. It's driving on a flat road, so therefore Fn is equal to Fg, which is equal to mass times gravity, which is then going to be equal to 0.6 times by the 1,000 times by 10, which should be equal to 6,000 newtons. Now, it's a question about whether it will skid off the road. So we need some reason why it's not going to skid off the road. So as our force of friction is greater than F net, will not skid off road. Next part, so part C, determine the maximum coefficient of friction required for the car to skid off the road. So the easiest way to do this would be to find the coefficient of friction that still meets that requirement. So we're going to look at when our force of friction is going to be equal to F net. Mu Fn is going to be equal to our F net. Fn in this situation is still driving on a flat road, so it's going to be equal to Fg. So our mu Fg, which is then going to be equal to mg, mu mg, and this is all going to be equal to mv squared on r. Mass is going to cancel in this situation, so we're ending up with our coefficient of friction equal to v squared on rg, which would then be 14 squared on our radius of 50 times by 10 for our gravitational constant. This number comes out to be 0.392. However, that's the minimum amount of friction to actually keep us on the road. Therefore, to skid off, mu is less than 0.392. Make sure that you actually address the question. It's actually determine the maximum coefficient required to skid off the road. We found the minimum amount of friction that will actually keep it on the road. Part D, we need to drive around a bank corner. So looking at the car traveling at us head on, we would have an angle theta here with a car that is driving towards us at this point. If I draw this as a free body diagram, I would have a gravitational force pointing down and a normal force pointing towards the center. If we look at the components, that angle in here would be equal to theta. It's not moving up or down the ramp, it's remaining at that center point, so the sum of the forces in the y is going to be equal to 0. There are two components there. That's going to be the Fn in the positive direction, but it's only the cosine component of it. So cosine of theta minus the force due to gravity. We could substitute in the mass, gravity, but we don't know what the normal force is, and we don't know what the cosine component is going to be. So let's think about now the sum of the forces in the x. The x is where we're going around the circle. So that means that the sum of the forces in the x direction must be equal to our mv squared on r. There is only one force pointing us towards the center of the circle, and that is the normal force, but not all of the normal force. There is only a component on the normal force, which is this part up here. That means this is going to be equal to Fn sine of theta. We know what the velocity is, we know what the radius is, we know what the mass is, we don't know what Fn is, and we don't know what theta is. But we've got an Fn, a normal force, and a cosine of theta from our y. So let's rearrange for the normal force in our y direction. So that would mean that we get Fn cos theta is then going to be equal to our force due to gravity. Fn is then going to be equal to our force of gravity divided by our cos theta, which we can now substitute into the equation below. So that means that we would get Fg on cos theta, sine theta, which we could then substitute in our mass times gravity and convert a sine theta on cos theta to be tan theta. This means that we get mg tan theta. Our masses are going to cancel, then we are solving for theta. So we're going to get v squared on r is equal to g tan theta. Solving for theta, we get theta is then equal to the tan inverse of v squared on rg, which we could then plug our numbers in. 14 squared on 50 times by 10, which should come out as being our answer of 21.4.